Section 4.4, what we've been waiting for all year, the fundamental theorem of calculus. The, not a fundamental, fundamental, it's fun, and we get mental, duh, theorem of calculus. Fundamental, everything based off of this. Of course, everything's really based off of the limit, but the next thing everything's based off of is this. So differentiation, the slope of the tangent line to a curve, and integration, area under a curve, that's a very loose description there, are inverse operations just as multiplication and division are inverse operations. Now we know that slope is delta y over delta x, and we know that area is delta y times delta x. So what the fundamental theorem of calculus says, if f is a continuous function on the closed interval a to b, and cap f is an antiderivative of f on the closed interval a to b, then the integral from a to b of f of x dx is cap fb minus cap fa. In other words, the change that occurs on my function cap f can be determined by integrating the derivative and evaluating that antiderivative at the endpoints and finding the difference. Now, if we took this equation and rewrote it looking for f at b, then I could add f at a to the other side of the equation. And notice another way I could think about this is that cap f evaluated at b is, watch this, where I was, the y value where I was on my function at a, plus how much that function changes on the interval from a to b. Now this is a very useful interpretation. Okay, so you can evaluate a definite integral without using the limit of a sum. It is not necessary to include or find a constant of integration, c, in our antiderivative. Our first example, we're going to integrate 3 dv with respect to v on the interval from 2 to 7. My antiderivative function is 3v, and this symbol says we're going to evaluate from 2 to 7. And that means 3 times 7 minus 3 times 2, using our fundamental theorem of calculus. And that gives me 21 minus 6, which is 15. Okay. Another way to write this is we could have pulled that 3 out and then just dealt with the v inside. And that would be 7 minus 2, then times the 3 at the end. Now, what is going on? We know our function of v would be 3v plus some constant c, right? Here is our derivative function, the line y equals 3. We can see that the area under that curve would be 3 times 5, which is 15. So now we're going to see why we don't need to do the plus c when we are doing what is called a definite integral. If we had evaluated this with the plus c, what happens is I have 3 times 7 plus c minus 3 times 7 plus c. Distributing that negatives takes this plus c and this minus c, and they drop out. So we don't need that plus c when we're evaluating a definite integral. All right, let's look at the next example. Integrate the function negative 4x plus 4 with respect to x on the interval from 2 to 5. So we know that this is going to give us negative 2x squared plus 4x. You're all pros by now at doing the anti-differentiation. From 2 to 5, substitute 5, that goes first, substitute 2, f of b minus f at a. Now, you'll notice that I have a lot of aloha going on, and it's not algebra this time, it's arithmetic. So we've got to distribute that negative, so let's do the work inside the parentheses first, okay? Then we'll worry about the negative. So we would say that the integral from 2 to 5 of negative 4x plus 4 with respect to x is negative 30. What does that mean? On the interval from 2 to 5, my antiderivative function of this decreases 30. Let's look at what that graph looks like. Here is negative 4x plus 4, my derivative function. From my derivative function, I can tell what my antiderivative function is doing. And you can see on the interval from 2 to 5, I have a nice little trapezoid there. I can find that area. But I have all negative values. So that helps explain why we are decreasing so much on our antiderivative function. All right, now this can just get a little bit messier. I could have, noticing that I have a -2 in here, I could have factored a -2 out of there and gotten this, and then substituted my 5 in and substituted my 2 in, and then do all that work. I think this wasn't terrible here, but I really do believe it's a good idea whenever you have a common factor that is a constant, not a variable. You cannot bring a variable out of here, just as you cannot bring a variable out from behind the integral sign. But when you have a common factor, bring it out and deal with that multiplication at the end. Now, the success that you have on this is really just going to depend on how good you are at anti-deriving. All right, so let's look at this next example. We might want to do some simplifying before we move on with it. So the square root of 2 over x could be considered the square root of 2 over square root of x. Okay, and now that would be the square root of 2 times x to the -1/2. And I can bring that square root of 2 out in front. You can see that that would be definitely something we might want to do. Then we're going to do the antiderivative. Remember, add 1, that makes it 1/2. Dividing by 1/2 gives you the coefficient of 2, okay, on the interval from 1 to 8. And I am doing my work in the way that I tell y'all I don't want you to do it, which is horizontally. I want you working vertically like this, but I didn't leave myself enough room to do it, so there you go. All right, what else could we do? We could take that 2 there and factor that out. And now I've got something really nice and easy to work with. We are going to substitute our upper limit in, 8 minus 1, each of those under the radical. The square root of 8 is 2 square roots of 2. Of course, the square root of 1 is 1. So now 2 square roots of 2 times 2 square roots of 2 is 4 times 2 minus 2 square root of 2, and all I can do is just simplify that. 4 times 2 is 8. Now another way I could have done this is just to do 2 times the square root of 16 minus 2 times the square root of 2 times square root of 1 is still square root of 2. And then I would have to do the square root of 16. So lots of ways to think about it. Now let's look at a trig one. All right, again, you have to be very careful when you're anti-differentiating your trig functions because you really need to know them. Let us remember, cosine is the derivative. It came from sine. So the antiderivative of cosine is sine. And we're going to evaluate from 0 to pi over 4. So the sine of pi over 4 minus the sine of 0, we know that this is square root of 2 over 2 minus 0, which is square root of 2 over 2. Could you have left your answer as 1 over square root of 2? Sure. Here we are evaluating on our unit circle from 0 to pi over 4. So how much did the y coordinate of our function change? Square root of 2 over 2. Or I could think about what does sine look like on the interval from 0 to pi over 4. That's how much my y value changed. Square root of 2 over 2 units. This is an example where I'm going to ask you to listen to the explanation all the way through before you write anything down. Then I will give you the time after I explain it. But the continuity of your attention matters. Notice we have an absolute value function in our integrand. So we know what x squared minus 4x plus 3 looks like. We know that when we factor it, I'm going to have zeros at 1 and 3. My vertex is going to be halfway between our zeros at 2. We're going to have a y-intercept when x is 3. So we can see that my function x squared minus 4x plus 3 is going to look like this. What does the absolute value piece do? It takes the part below the x-axis and flips it above the x-axis. So my actual absolute value function is going to look like this. What property did we just use? When the quantity inside is not negative, which happens when x is less than or equal to 1 or greater than or equal to 3, the absolute value of that thing is itself. When the quantity inside the absolute value bars is negative, its absolute value is the opposite of itself. So that is the importance of being able to work with an absolute value function. Now we're going to anti-differentiate it. Now you'll notice for the integrand, I'm going to, from 0 to 3, integrate the function as it appears, and from 3 to 4. I went back to my polynomial form because, of course, that's easier to integrate than our factored form. But what about from 1 to 3? From 1 to 3, this polynomial dips below the x-axis. So I have to negate that part that is below the x-axis from 1 to 3. So my integrals actually look like this. From 0 to 1 and 3 to 4, I have the same thing, and then subtract from 1 to 3 because that's going to be a negative area, but I got to count it positively because of those absolute value bars. Now we're going to anti-differentiate each piece, and that's real nice and easy to do because they all have the same antiderivative. Now we're going to evaluate each from 0 to 1, substitute 1, minus, substitute 0. Cool, we know that's going to be 0. Okay, then from 3 to 4, substitute 4, minus, substitute 3. Again, be very, very careful in what you show with your work. Make sure you have your negative sign here and parentheses around the part that follows it. And then minus, substitute 3, minus, substitute 1. Now, when I substitute 1, we get 1/3 minus 2 plus 3. When I substitute 0, I get 0. So we have, let me suggest, do all of your arithmetic before you start converting to fractions. So this is going to give me 1/3 plus 1 in that parentheses. Now when I go from 3 to 4, substitute your 4 in, gives you this. Substitute 3 in, gives you this. Now this is kind of nice. 9 minus 18 plus 9, that's 18 minus 18, that's 0. So we're done with that. And guess what? That means over here where I have that same quantity, that's 0. Now, what can I do here? Negative 32 plus 12 is negative 20. Again, leaving this in fraction form. Maybe all my fractions will add up to a really nice number, and I never have to convert at all. Now I'm going to come down here, and this is from 1 to 3, so there's my 3, which I knew became a 0, and I've already done my 1 over here, so we know that's 1/3 plus 1 inside the parentheses. And now, let's do some evaluation. Now, I actually am going to work this problem a little differently in a minute, but just finishing this workout, this gives me 4/3. This gives me 64/3 minus 60/3, and this over here is 4/3. So that's 4/3 plus 4/3 plus 4/3 is 4. Yay. But let's go from this point right here, this line, and let's group together the fraction terms and the integer terms. So I have 1/3 plus 1 plus 64/3 minus 20 minus 0 plus 1/3 plus 1. All right, that's a 1/3 and a 64/3, and a 1/3 is 66/3. Cool. 1 minus 20 plus 1 is 2 minus 20. That is minus 18. 66/3 is 22. That gives me 4. Look at that. I never had to do any fraction conversions at all. I would say this is really cool. And what was really cool? No fraction conversion. So that is cool, too cool for school. Okay, pause your video and write down what you see nicely and neatly. More continuing to write down all of the work. The added too cool for school. Now we come to our fourth existence theorem. What existence theorems have we had? We have had the intermediate value theorem. We have had the extreme value theorem. We have had the mean value theorem. And now we get the mean value theorem for integrals. An existence theorem, a theorem that tells you something exists. It does not tell you how to find it, but it says if you satisfy these conditions, then here's what you can do. Mean value theorem said if a function f was continuous on the closed interval and differentiable on the open interval, then there was some c in the open interval from a to b where the derivative at c was equal to the average rate of change from a to b. The slope of the tangent equals the slope of the secant. Mean value theorem for integrals deals with areas. Instead of slopes, it deals with areas. And it says if our function f is continuous on the closed interval from a to b, then there is some number c in that closed interval from a to b such that the integral from a to b of f of x dx is equal to f at c times b minus a. The height of our rectangle times the width of our rectangle. What? So let's go back to our rectangles. If I look at this curve right here, here's my curve, okay? Some function. Here's my interval from A to B. If I look at my left-hand rectangle, it's this one. That is way underestimating this area under the curve. If I look at my rectangle formed by the right endpoint, that's this one. That is way too much. There's a lot of area being counted that is not under the curve. I like to call this the Goldilocks theorem because it tells us which one is just right. There is some c in this interval such that when I evaluate c on my function, I get a rectangle whose area is exactly equal to what is under the curve. Say that one more time. The mean value theorem for integrals says if f is continuous on the closed interval from a to b, then there is some number c in that closed interval such that the integral is equal to f of c times b minus a, such that the area under the curve is equal to the function evaluated at c times b minus a. The function evaluated at c gives me the height of that rectangle. B minus a gives me the length of the rectangle. Now, notice Goldilocks. The inscribed rectangle was too small, too little. The circumscribed rectangle was too big. The mean value theorem rectangle, just right. The value f of c is called the average value. That is our average value. How could I get this equation solving for f of c? I could just divide by b minus a. One more time. How can I find this f of c? How can I find that mean value, that average value? Mean means average. How could I find that value? Value is the y coordinate on the function. How could I find that y coordinate, which is going to give me my average, my best, just right rectangle that equals the integral, the average value? If f is integrable on the closed interval from a to b, then the average value of f on the interval is 1 over b minus a times the integral of a to b of f of x dx, or the integral from a to b of f of x dx divided by b minus a. It is just changing that up. But you need to recognize that this simply means we're looking for that. This means we're looking for f at c. That is our average, dividing by b minus a, our average value. Very important. So let's look at an example that does this. Sketch the graph of a function over the specified interval and find all values of x on the closed interval a to b, which satisfies the average value. Now here's my integrand function on the closed interval from a to b. So we want this. Okay, there's what we're going to write up. Now, you don't know how to integrate a quotient, and so we need to rewrite this, and we can think about this function instead of as a single fraction, write it as two fractions, and those two fractions, this one reduces, and this one can be written as 4 times x to the negative 2. Now, our average value, average because I'm going to divide by b minus a, value of the function is f of c, average value is the integral from a to b of our function divided by b minus a. Now you can see there's a lot of little messy work we can do. If I just perform the integral of the numerator and I take care of that, that is going to give me x plus 4x to the negative 1 over negative 1, which is really going to be x minus 4 over x. Notice I have to integrate and simplify before I evaluate. Do you know that the most common mistake students make is they start evaluating, but they have forgot to integrate. They didn't anti-differentiate that function. Again, I'm working this problem horizontally because I did not leave myself enough room to work it vertically, but we all got to work on that. Substitute our 2, substitute our 1/2. This is going to give me 2 minus 2 minus the quantity 1/2 minus 4 divided by 1/2 is actually 4 times 2, which is 8. And that's going to give me 15 halves. Now, we're not done. That's just the numerator. Divided by 2 minus 1/2, that's 4 halves, minus 1/2 is 3 halves. So I have 15 halves divided by 3 halves, which is 15 halves times 2/3, which is 5. Now, what is 5? 5 is my average value. 5 is the y-coordinate where I will have a rectangle whose area is exactly equal to the value of that integral. One more time. 5 is my average value. Average divided by b minus a, value, y value on the function that will give me a rectangle whose area is exactly what is under the curve. Now, what if I want to know what x-coordinate gave that to me? Right? Well, then I'm just going to go to Algebra 1 and solve that equation. When does my derivative function f of x equal 5? What x-coordinate will give me a result of 5 in my function? Well, you know how to do that because you passed Algebra 1. So I would write this as 1 plus 4 over x squared equals 5. Subtracting gives me this. Notice that when I have 4 over x squared equals 4 over 1, I can just flip both of those fractions. Isn't that cool? And this gives me x squared equals 1. You must solve the equation properly, then exclude. Do the correct mathematics, then exclude. Why do we exclude -1? Because the value you solve for must be on, in this problem, it is the closed interval. In the mean value theorem for integrals, it must lie on the closed interval. In the mean value theorem, your value you find for x must lie on the open interval. This must lie on the closed interval. All right, see example 5 for a Riemann sum approach. We'll actually look at this after I teach some Riemann sums with the limiting approach. And then this next part of the lesson will be taught live in class. Live calculus. Don't miss class. Your 4.4 TPs, 5, 9, 13, and 43. See you next time.